Hello. In this video, we are going to discuss about the numericals that we'll be performing for the Bohr-Sommerfeld theory of hydrogen atom. And to start with, the first bit asks us to calculate the speed of the electron in the nth orbit of the hydrogen atom. And if the relativistic correction is important for V over C being greater than 0.005, we wish to find for which orbit this correction is necessary, and we have been given the data regarding the charge of the electron, the Planck's constant, the velocity of light, as well as the permittivity of free space. So in order to do that, first of all, we need to put forward the conditions that we have at hand, where the first condition implies the mechanical stability of the electron, while where we are comparing the centripetal force that is available for the electron due to the electrostatic force of attraction between the nucleus and the electron in case of hydrogen atom, Z being equal to 1. So there's the mechanical stability, and then we consider the quantum condition, and by taking the ratios we get the expression for velocity, which is as follows. And with this available to us, we can just substitute the values and get the expression for velocity, which is of course of the form of the velocity in the first orbit, that is 2.18 times of 10 to the power 6 meters per second, over n for the nth orbit. Now with this condition available to us, we further move into the next part of the question, which says that if the relativistic correction is important for any value of V over C being greater than 0.005, then what must be the orbit where the correction will be necessary? For that, we take the value of V over C, the V that we have obtained over here, and the C that has been given to us, and from that we calculate the value of n, which gives V over C to be equal to 0.0073 over n. Now n can have these values, n is equal to 1, 2, 3, it goes on, and from that what we get to know is that for n is equal to 1 only, V over C is going to be greater than that factor that has been provided, that is 0.005. For other values of n ranging from 2 over 3, then so on, the values will be less than 0.005. You can check for yourself, and that is why the orbit, that is the relativistic correction, is necessary for n is equal to 1 orbit. In the next bit, we are to obtain the number of revolutions that the electron in n is equal to 2 state makes within a hydrogen atom before dropping to n is equal to 1, which is its stationary ground state. The average lifetime of an excited state is usually 10 to the power minus 8 seconds. And the value of the Rydberg's constant for the infinitely heavy nucleus consideration has also been provided to us. Let's see what we can do. Now, first of all, we must consider again the mechanical stability of the electron and the quantum condition, and use it as we have used in the above case, and using them we determine the value of V as well as the radius in that case. And in this case, the radius that we'll be considering, obviously that will be a circular radius, because the hydrogen atom consists of a circular comprises or has the electron to be moving along a circular path. So we'll be considering both of them and obtaining the value of V and R at first. Having obtained those values, we now focus on the frequency. Now the frequency gives the number of revolutions per second in the orbit, and the frequency, which is 1 over time period, is definitely going to be the velocity over the total distance. Now the total distance, as we know, is going to be a circular path. We have the radius, so we are going to take the circumference of the circle as the distance covered by the electron, and the velocity over the distance covered is going to give me 1 over time period, which is the frequency, that is the number of revolutions per unit time. From that we obtain the value in terms of the Rydberg's constant, which is equal to Rydberg's constant for the infinitely heavy nucleus consideration multiplied to 2c over n cube. Now we put the values for n is equal to 2, that is the state in which it is orbiting, and we check for the frequency, and thereby the number of revolutions can therefore be obtained by multiplying it with the time limit that has been set, that is the lifetime for the excited state. So we obtain the number of revolutions in 1 second, as I said, and the number of revolutions in 10 to the power 8 seconds minus 8 seconds, that is the lifetime that is provided, or the lifetime value that has been provided for the excited state, and that when multiplied to the number of revolutions in 1 second is unitary method, is going to give us 8.2 times of 10 to the power 6, which is the number of revolutions that it must make in that given lifetime, which is what we were required to obtain. For the next bit, we wish to calculate the wavelength of the 8th line of Bohr series of the hydrogen atom, where we have been provided with R infinity to be equal to 1.09737 times of 10 to the power 7 meter inverse. Now, the common formula, the formula where we are obtaining or we are giving for the Bohr series, is given as follows, that is the wave number, or the reciprocal of the wavelength, is equal to the Rydberg's constant for the hydrogen atom. And remember, it is RH, not R infinity. You should have that in mind. And then that multiplied to 1 over 2 squared, because the Bohr series starts from n is equal to 2 and it extends for n is equal to 3, 4, 5 and so on. But what we wish to obtain here is the 8th line, so we have to go a bit further, that is 5, 6, 7, 8, 9, and when we move to the value 10, it continues for sure, but when we move to n is equal to 10, then we have the 8th line over there, because obviously n cannot be equal to 2, because the Bohr series starts for the first n1 to be 2. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 10 is the 8th value over there, and that is why that will give the 8th line. And to calculate the wavelength, we simply put n is equal to 10. So we have 1 over lambda to be equal to, and that is to be equal to 6 RH times of RH divided by 25, and that's for the 8th line. Now, because we know the relation that the Rydberg's constant RH is going to be R infinity over 1 plus the mass of the given electron over the mass of the nucleus. In this case, the nucleus only contains the proton in case of the hydrogen atom. So, and we know R infinity is for the infinite mass consideration of the nucleus. So here we wish to substitute the values of m and mh, and we know that the ratio over there, m over mh, is going to be 1 over 1836. So the Rydberg's constant that has been provided, which is 1.097 times of 10 to the power 7, that is for R infinity, plus we have the value of m over mh to be equal to 1 over 1836 as discussed in the theory section. So we have the final value of this Rydberg's constant over here to be equal to 1.09677 times of 10 to the power 7 meter inverse. And if we substitute that value over there, we are going to get lambda to be equal to 25 over 6 times of that value that we have just obtained for RH, and we put that value over there and we obtain the value of lambda to be nearly equal to 3799 angstrom units, that is 10 to the power minus 10 meters. In the next bit, we are supposed to find the energy, momentum and wavelength of a photon emitted by a hydrogen atom making a direct transition from an excited state with n is equal to 10 to the ground state, which is obviously n is equal to 1. And then we are also to find the recoil speed of the hydrogen atom in the process that occurs. So in order to do that, first let's calculate the energy. We have the expression for energy of the hydrogen atom, which is as follows. So from that, if we put the values of RH and H and C, which are all constants of course, we get the value as 13.5 electron volts. Now we'll be getting this in joules of course, but we can it is ideal for us to convert them to the electron volt unit in case of the measurements involving the energies in the atomic level. So it is any joule that has been obtained, any joule amount of energy must be divided with 1.6 times of 10 to the power minus 19 to give the value in electron volt. And having obtained the energy, now we can calculate the momentum of the photon, because the momentum simply involves the energy over the velocity. So that's what we are going to get. So we again convert the energy back to joules, and then we divide it with the velocity of light, or the photon in this case, and we have the value to be 7.2 times of 10 to the power minus 27 kg meter per second, the momentum of the photon. Now to find the wavelength of the photon, we see that the atom drops to the ground state, that is n is equal to 1, as I said earlier, and hence the photon emitted belongs to the Lyman series, and the wavelength of the spectral lines in the Lyman series can be given as follows. And having applied that case over there, we get lambda to be nearly equal to 921 angstrom units. Now finally, the emission of the photon will result in the hydrogen atom to recoil, and it recoils with a certain momentum of course, and well, the momentum will be the same as far as the conservation laws are concerned. So the conservation of linear momentum has the case of the recoiling of the hydrogen atom to have the same momentum, that is the momentum that is possessed by the photon. And so we can calculate now the velocity of recoil. So the recoil speed, in this case recoil speed of hydrogen atom, that is we will be taking the momentum of the hydrogen atom, which is the mass of the hydrogen times of the velocity, and that momentum will be equal to the momentum that has been obtained, that is 7.2 times of 10 to the power minus 27. And finally we have the velocity to be equal to 7.2 times of 10 to the power minus 27 over the mass of hydrogen being the mass of proton in this case as for the hydrogen atom. So we have that to be 1.67 times of 10 to the power minus 27, and that equates to finally a value of 4.31 meters per second. That's the value of recoil speed of the hydrogen atom in this transition. Now in the next bit we have a photon which ionizes a hydrogen atom from the ground state. Okay, and the liberated electron, because of the ionization, as it goes up, it recombines with a proton into the first excited state, thereby emitting a 466 angstrom photon. So what we need to find is firstly the energy of the free electron, and secondly the energy of the original photon, which was responsible for all of that. Now the photon, what it did is that it provided with sufficient energy to an electron in the ground state, thereby releasing it or making it free. But the electron, while it was traveling, it got stuck in the first excited state, it recombined, and the excess of energy after that recombination, it gave away in the form of a photon which was 466 angstroms in wavelength. So that's the story of it. Now we wish to obtain the energy of the electron and the energy that the original photon had. So let's get started. Now, because we have the case of the electron in the first in the ground state, now we need not use those values that have been given to obtain the energy of the electron in the ground state, because we know that the electron will possess an energy um, in any given nth state to be of the order of minus 13.6 electron volt over n squared, and for the ground state n is obviously equal to 1, and that's what will be the energy, which is minus 13.6. Now in the first excited state we have the energy. First excited state means n is equal to 2, that is going from n is equal to 1, the ground state, to the first excited state. The energy that it will possess is E2, which is equal to minus 13.6 over 2 squared, that is 4, and that is going to give me minus 3.4 electron volt. Now that is the energy that is possessed by the electron in the first excited state. Now what about the energy that has been emitted, the energy of the photon? Now the energy of the emitted photon with a wavelength which is 466 angstrom, that will be equal to hc over lambda that we know, and that is going to be equal to, if we put the value of h, the value of c that has been provided to us, from that converting, it is always ideal to convert it into electron volts, and converting into electron volts we get 26.7 electron volts. You can put the values and check for yourself. This is what we are going to obtain. Now the total energy therefore of the liberated electron that has been asked in the bit that in the first place, that is the energy that is possessed by the free electron, will be a combination of both of them, because it will have some energy in the first excited state, which is this, and the energy that it has, the excess of energy that was released upon a recombination, was this. So the total energy of the free electron when it was liberated will be equal to the sum of both of these, that is a minus 3.4 electron volts plus 26.7 electron volts, which in all gives me 23.3 electron volt, which is positive energy, of course. Now as far as the so this is the first case that we have obtained. Now as far as the total energy of the photon in original, which supplied the energy to the electron in the first place, when that is to be obtained, now in order to just excite the electron, in order to ionize, that is, the electron in the ground state, now the energy that is possessed in the ground state by the electron is going to be minus 13.6 over 1 squared, so that is minus 13.6, which is the energy possessed by the electron, and the energy that needs to be supplied will be exactly that much, but in positive, because the bound state has to be free, so the total energy of the electron has to be 0, and so the energy in order to ionize the electron in the ground state will be equal to the positive value, which is 13.6 electron volts. I hope you understand this. Now with that energy that has been provided, the electron further has an excess energy, the free electron has an excess energy, and that energy has obviously been provided by the photon. So the photon in all has or had provided not only the energy to ionize it, but also the energy to which is left over, that is 23.3, after all those energy considerations in the first excited state, and as well as the energy of the photon that was emitted. So the photon in all had provided with an energy of the sum of these two, which is 23.3 electron volts plus the 13.6 electron volts, which results in a total of 36.9 electron volts in total to the electron to do all such things. So this is the thing that we were to find in the second place, that is the energy of the original photon. Up next, we have a beam of electrons to be bombarding a sample of hydrogen. Now, through what potential, minimum potential difference, must these electrons have been accelerated if the first line of the Balmer series is to be emitted? Now, for the first line of Balmer series, we know that it goes from n is equal to 1 to n is equal to 3. And so the corresponding energy as well as the potential difference is to be obtained. So we will see that, and then we have to explain how many possible spectral lines can be expected if the atom finally attains the normal state. The normal state, which means the ground state of the electron, which is in case of hydrogen, it is equal to n is equal to 1. Now, as for this value, this condition that we have at hand, the electrons that are bombarding into the sample of hydrogen, they must have been accelerated through some potential difference. Now, if we apply a certain potential difference to a beam of electrons, then only can they accelerate, else they won't. So supposedly we have a potential difference over here, which is this is the negative side and this is the positive side. We have a potential difference, supposedly V volts, and an electron is present over here, so it is definitely going to accelerate towards the positive plate. And in the process, if we place a sample of hydrogen atom over here, what it's going to do is it is going to strike it, and in the process it may cause the electrons that are present, or one of the electron that is present in the ground state, that can raise up and move to a higher orbit. And in this case we wish to obtain the condition or the potential difference which has resulted in the electron to provide the first line of the Balmer series. Now, for the first line, the solution is as follows: that for the first line of Balmer series, we have that to be the condition over there is simply RH. The difference in energy is obviously E1 minus E3, because as for the Balmer series. But hang on, we wanted to, for the Balmer series, we know it is from 2 to 3, but we must also know that because the hydrogen atom was not in any excited state, it was in the ground state for sure, and then from that ground state it will be taken through to n is equal to 3, and in the process as it returns back to its ground state, as it heads towards the ground state, in the process it is going to land over n is equal to 2. There is a possibility that it will go from n is equal to 3 to n is equal to 2. So let's see the diagram over here, this energy level case. So we have n is equal to 3 over here, n is equal to 2 over here, and n is equal to 1 over here. So the electron that was present in that ground state now probably has achieved the energy and moved over to n is equal to 3. Now, as it has moved to n is equal to 3 over there, while staying there fractionally for a very small amount of time, it returns back, and it may happen that it will return from n is equal to 3 in steps to n is equal to 1. That is, firstly from 3 to 2, and then from 2 over to n is equal to 1. Or it can take a direct case where it is moving from n is equal to 3 to n is equal to 1. Now, that may be the case as well. So here we already have the second part of the question that asks us how many possible spectral lines can be expected if the atom finally attains the normal state, which is to the ground state. So the possibility of achieving this is, there are three possible ways, of course, from n is equal to 3 to n is equal to 2, then from n is equal to 2 to n is equal to 1. So this is one possibility. Or we have after it, so this is one possibility, which means this is one line and this is another line, and because it has asked the possible spectral lines, so from n is equal to 3 to 2, one spectral line, and n is equal to 2 to 1, there will be another spectral line. And then if it has moved from n is equal to 3 to directly n is equal to 1, we can have another case of the spectral line. So this is not a case of single electron. There will be electrons involved. There are a lot of electrons, a lot of atoms in a given hydrogen sample, and therefore we are expecting at least the case of possible spectral lines that we can expect are 3, and all these spectral lines will be in that range. So that will be the number of spectral lines that we can expect. Now, as for the first part, so we can understand that E, the energy difference, has to be taken from the ground state to n is equal to 3 state, and for that we will be calculating the value, and that is the direct value that we have for that, which is minus of RH times of H times of C, because this is the energy that we are obtaining, not 1 over lambda. And for n is equal to 1 to n is equal to 3, and this is something of the value 8 over 9, and negative multiplied with negative is obviously going to be positive over here. So 8 over 9 RH times of HC, we put the values that we know of, and from that we calculate the value of E1 minus E3 in electron volts. Of course, that comes out to be 12.1 electron volts. So this 12.1, now it is, now you will see the use of converting them to electron volts. So because this is the amount of energy that the electron must possess, so we have the electron must be accelerated through a potential difference which is numerically equal to the energy, in this case, which is obtained in electron volt, and that is 12.1 volts, because one electron will possess an energy which is equal to charge multiplied with the voltage. Charge of the electron is 1e, in this case the unit value that we take, so 1e into that many volts is giving me 12.1 electron volts. So it is ideal every time to calculate the energy in the atomic level in electron volts. So we already have discussed the second part of the answer, which involves 3 spectral lines in all that we can expect the possibility, and so that is for this bit of the question. Moving over, now in the seventh bit we have a positronium atom. Now, what is a positronium atom in the first place? The positronium atom has the positron and the electron revolving about their common center of mass, and therefore the common center of mass lies halfway, because the positronium with the positron, which is of the same mass as that of the electron, it's antiparticle, and when they set up an atom where the positron and the electron are revolving about the center of mass, that is the positronium atom, and we wish to calculate or compare its ionization energy and emission spectrum with that of hydrogen atom, considering the infinitely heavy nuclear mass. Now, for this, first of all, we must consider obtaining the reduced mass. Now, the reduced mass in this case will be because the positron and the electron have the same mass, the reduced mass is obviously going to be half of it, which is obtained like this. That is the product divided by the sum, which is m over 2. Now, with this reduced mass uh, of the electron, the uh, the reduced mass of electron in hydrogen obviously is nearly m. So now the Rydberg's constant for positronium, which will be Rp, that is definitely going to be equal to half of that of R infinity, because we are going to substitute Rp, that is equal to the reduced mass times of e to the power 4 instead of R infinity, which is m times of e to the power 4 in that case. So this is the value of Rp, which is the Rydberg's constant corresponding to the positronium. Now, with this information available to us, we can therefore calculate the energy of the positronium atom, and in that case, the energy of the positronium atom in the nth state, of course, is going to be minus of the Rydberg's constant corresponding to it, z square hc over n square, and because we are comparing it with the hydrogen atom for which z is equal to 1, so for H atom, as z is going to be equal to 1, we have the energy corresponding to that to be equal to minus RH times of z square hc over n square. Now z goes to 1 for sure. Now with z going to 1, if we use these values or compare these values, these are the energies that are possessed, and hence the ionization energy, which is equal to, numerically equal to these values, instead of the negative sign, of course. So we have the ionization energy of positronium to be half of that of hydrogen, because as you see, there we have Rp and here we have Rh, and we know that Rp is equal to half times of R infinity, which is the case over here for Rh, because it has been provided that we have the H atom with infinitely heavy nucleus. Now, in order to calculate the spectral lines, the comparison of the emitted spectral lines in case of positronium to that of hydrogen, we just need to calculate the wavelengths concerned. Now, as for positronium, we have 1 over lambda p to be equal to Rp times of 1 over the final square minus the initial square, and in case of hydrogen, we have 1 over lambda h to be equal to R infinity over here, and the same thing 1 over nf square minus 1 over ni squared. And so taking these ratios, what we obtain from them is that lambda p over lambda h is going to be equal to 2, because Rp over Rh, that is R infinity, of course, so this is R infinity over Rp that we are going to have, and that is going to be equal to 2. So the wavelength of positronium lines are double than those of the hydrogen lines, which is what we were supposed to obtain in the second case, that is for the emission spectra. So that's it from this segment of the atomic and molecular spectra. The theory that we have so far used has been provided, and we have considered the corresponding numericals associated with them. There are many more. You can try them for yourself from by yourself from different authors, different books, or even if it is provided to you in some university assignments or something like that, previous year questions. So you can try them, and we can discuss them if you wish to share them. So care to share. Till then, thank you for watching.